Imagine flying over the vast Pacific in 1943. The air is hot, the humidity wraps around your aircraft like a wet blanket, and somewhere below, a Japanese fighter might be climbing toward you. Now imagine something even more dangerous. The engines that keep you alive are beginning to overheat. For Allied pilots in the Pacific theater, this wasn't just a technical inconvenience. It was a daily threat, one that could seize an engine, destroy a mission, or end a life long before a single bullet was fired. And the solution to this deadly problem came from a design change so simple, so understated, that most people today have no idea how revolutionary it was. The hollow steel Hamilton Standard cuffed propeller. To appreciate why a steel propeller cuff could change the course of the air war, we need to understand the brutal environment in which American aircraft operated. European airspace was cold, thin. Frigid temperatures at altitude acted like a natural coolant. But the Pacific, it was the opposite. Tropical heat, thick, wet air, endless sun. High-powered engines pushing heavy, long-range aircraft created heat loads far beyond what their original cooling systems were designed to handle. American aircraft, particularly early versions of the P-40, P-47, and above all the P-51B and P-51C, could run dangerously hot during long climbs and low-altitude combat. Pilots complained of needle-pegging temperatures, boiling coolant, and engines that fought against the environment as much as they fought the enemy. Engineers needed a solution. A better radiator? Too heavy. Bigger oil coolers? Not enough airflow where it mattered. More vents or scoops? Aerodynamically costly and often ineffective. What they needed was a way to force a stronger stream of cooling air directly into the engine compartment, without redesigning the whole aircraft. That's where the hollow steel Hamilton Standard propeller cuff came in. Originally, the cuffs on many propellers were simple aerodynamic fairings, designed to smooth airflow across the blade route. They weren't there to cool engines, they were there to reduce drag. But Hamilton Standard engineers realized something brilliant. These cuffs could redirect airflow, scooping large volumes of air and forcing it directly into the engine's air intake and cooling pathways. A properly shaped cuff could act like a ram air amplifier. That idea wasn't theoretical, it was tested rigorously. And in the Pacific, pilots found that the difference between a cuffed and uncuffed propeller could be the difference between a smooth-running engine and an overheating nightmare. The key innovation was this. Hamilton's cuffed design used hollow steel construction that allowed a very specific contour and thickness without excessive weight. Aluminum of the era couldn't achieve the same balance of strength, shape complexity, and durability for a part that sat at the base of a giant spinning blade. Steel let the cuff hold its shape at high speeds and handle enormous centrifugal forces without cracking, fatiguing, or deforming. And because the cuff was hollow, it didn't become a heavy weight that unbalanced the propeller. This structure allowed Hamilton Standard engineers to build larger, wider cuffs that acted like mini air scoops, channeling air with surprising efficiency. Pilots who tested the new cuffed propellers noticed almost immediately that their engines ran cooler on climb. Overheating during taxiing and ground operations dropped noticeably. Combat power could be maintained longer. The airflow pattern around the nose changed in subtle but crucial ways, especially on aircraft whose cooling systems depended heavily on ram air pressure, such as the Merlin-powered P-51. What made the cuff truly remarkable wasn't that it helped cooling a little, it's that it helped cooling enough to influence tactics. Long climbs over tropical islands, hard turns at low altitude, high-power chases that would have cooked earlier engines. These became more manageable because the cuffs literally pushed more air where it was needed. To understand why this mattered so much, imagine a pilot launching from a rough coral airstrip. He's loaded with fuel, ammunition, and the tropical sun is punishing the aircraft even before takeoff. He pushes the throttle forward. The propeller bites the air, and the aircraft lurches forward. But without sufficient airflow through the radiator and oil systems, the engine, the heart of the aircraft, could begin to fail before the wheels even left the ground. The cuffed propeller gave that pilot something priceless, a margin of safety, a greater cushion before the temperatures spiked into the red, a better chance of getting airborne without cooking the engine. In the Pacific, where distances were vast and emergency landing areas were rare, that margin meant survival. You can almost hear the difference when pilots described the change. Reports from the field came in, better cooling on climb, temperatures holding steady where before they would rise, engines running cooler at military power. These weren't small anecdotes, they were operationally significant. The propeller cuff turned out to be a targeted, aerodynamic solution that worked across a range of aircraft. And because it required no major redesign to the airframe, it could be implemented widely and quickly, an enormous logistical advantage during wartime. The cuffed propeller didn't make American aircraft invincible. It didn't eliminate overheating in every situation, but it cut down the frequency, and that changed the operational reliability of frontline fighters and long-range escorts in one of the harshest climates in the world. It's no exaggeration to say that thousands of pilots who flew long missions across the Central Pacific benefited from this underappreciated invention. With cooler engines came fewer failures, fewer forced landings, fewer aborted missions, and more aircraft that reached their targets and returned home. What's fascinating is how such a small aerodynamic feature plays into the broader story of wartime innovation. History tends to highlight the big inventions: radar, jet engines, nuclear physics. But war is often won by smaller, smarter adjustments. Improvements invisible to the public, but life-saving to the people who rely on them. The hollow steel Hamilton Standard cuffed propeller is one of those forgotten innovations. A small structural change that helped keep engines in the fight, helped keep pilots alive, and helped sustain Allied air superiority across a theater where mechanical reliability was as important as firepower. And perhaps most intriguingly, the cuffed propeller became part of the signature look of some of the most iconic aircraft of the war. When you see the silhouette of a P-51B idling on an island airstrip, sun glinting off the curved steel cuffs at the base of the blades, you're looking at an aerodynamic design born of necessity, one whose shape tells a story of engineering under pressure. Those cuffs aren't decorative. They aren't incidental. They are part of the reason those aircraft could take flight in places where engines struggled, where the environment punished every moving part, and where survival depended on every advantage engineers could create. So when historians talk about the Pacific Air War and the innovations that made victory possible, it's worth pausing to appreciate that sometimes the most important improvements aren't the ones that grab headlines. Sometimes they're the ones you'd only notice if you walked right up to the spinning propeller of a fighter plane and looked closely at the way its blades meet its hub. But the story doesn't end with the cuffs simply improving cooling airflow. To really grasp how important they were, we need to break down the aerodynamics behind them, the invisible, swirling river of air that a propeller creates. A high-performance aircraft propeller doesn't just push air backward. It reshapes everything around the nose of the aircraft. It creates a spiraling slipstream, low-pressure zones, high-pressure channels, and pockets of turbulence that can either starve an engine of cool air or feed it with a steady, refreshing stream. Before engineers introduced the cuff, much of the airflow at the root of the blade was chaotic and wasteful. The air wasn't being guided or shaped with purpose, and in the Pacific, that inefficiency could be fatal. The hollow steel cuff changed all of this. By forming a smooth scoop that blended into the hub, the cuffs acted like airflow shepherds. They grabbed air that would have otherwise passed uselessly around the spinner and redirected it into the cooling inlets and along the contours of the cowling. Instead of turbulence at the blade root, the cuff created a funneling effect, a controlled surge of air that blasted heat off the engine block, the oil cooler, and the intercooler pathways. Imagine placing your hand a few inches in front of a large industrial fan. You don't just feel wind straight on, you feel the temperature drop as airflow wraps around your hand. The cuff magnified that cooling effect, except instead of cooling skin, it cooled a high-powered, tightly packed, combat-ready aircraft engine. The truth is that the Pacific Theater exposed weaknesses in nearly every American aircraft design. Long-range operations meant long climbs to altitude. Escort missions meant escorting bombers for hours on end. Air combat over island chains meant low-altitude dogfights in thick air that made engines work harder and cooling systems less efficient. Even a seemingly minor overheating issue became a life-threatening problem when the nearest landing strip was hundreds of miles away. Pilots needed every minute of reliable engine performance they could get. And so the cuffed propeller didn't just enhance performance, it enabled strategies. The strategies to climb quickly to intercept incoming raids, the strategies to pursue enemy aircraft aggressively without fear of the temperature gauge turning red, the strategies to escort bombers deep into enemy territory without engines failing halfway. It's also important to recognize that wartime aviation was a constant tug-of-war between performance and survivability. Every piece added to an aircraft had to justify its weight, its drag, and its manufacturing cost. Engineers didn't have the luxury of designing perfect systems. They had to design the best possible systems that could be mass-produced, shipped halfway across the world, and maintained by young men on sandy airstrips with basic tools. The fact that the hollow steel cuffs became standard on so many aircraft speaks volumes. They proved themselves not only effective but practical. Strong enough to withstand vibrations and high RPMs, light enough not to compromise balance, simple enough to be produced at scale, and valuable enough to become a priority in upgrades and field installations. This brings us to another overlooked truth. The cuffed propeller wasn't simply a cooling improvement. It was a reliability multiplier. Many pilots in the Pacific flew missions that required pushing their engines to full or near full power for long stretches of time. Climbing to altitude wasn't a simple matter of gaining height. It was a challenge to prevent the engine from overheating long before reaching optimum cruising altitude. Before cuffs, engine temperatures often spiked during the first 10 to 15 minutes of flight. After cuffs, those temperatures became more manageable, giving pilots a bigger operational envelope. That meant pilots could climb faster without cooking the engine. They could fight longer without throttling back. And they could return from missions with engines that weren't on the verge of mechanical failure. And then there is the effect on morale. Pilots flying from remote Pacific outposts knew that technical failures often meant death, not because they would crash into populated areas, but because the Pacific was merciless. Miss an island by just a few miles due to an overheating engine, and you might ditch into an ocean where rescue was uncertain. Lose your engine halfway home, and the nearest friendly runway could be 200 miles away. Every mechanical improvement, no matter how small, was felt emotionally by the men flying those aircraft. When pilots realized their engines were running cooler, that they had a little more margin, a little more breathing room, the psychological impact was enormous. A pilot confident in his machine fought better, flew better, survived better. Some pilots later wrote about how they initially didn't believe the cuffs would make any difference. They looked too simple, too minor. They didn't have the glamour of new superchargers or more powerful guns. But after a few flights, the shift was impossible to ignore. A cooler running engine meant smoother performance and fewer scary temperature spikes during high-power maneuvers. And in combat, smoothness equals confidence. Now let's put ourselves into the cockpit of one of those aircraft. Let's say a P-51B Mustang operating from an island staging base in 1944. The Mustang's liquid-cooled Merlin engine was a marvel of engineering, but it was also sensitive. It thrived on cool, high-pressure air. In Europe, the engine loved the cold altitudes. In the Pacific, it struggled. A Merlin that ran too hot lost power rapidly. Boiling coolant could create vapor pockets, causing catastrophic engine failure within minutes. But with the cuffed propeller, the airflow into the Mustang's scoop increased. Ram air pressure improved. Cooling efficiency climbed. Suddenly, the P-51 could operate more comfortably in conditions that previously threatened to destroy its engine. The cuffs didn't magically turn the Mustang into a tropical super aircraft, but they gave it the edge it needed to perform in a climate that had previously limited its effectiveness. The innovation also played a role in the evolutionary lineage of American propeller technology. Later aircraft benefited from lessons learned in the Pacific, lessons that influenced propeller design, engine intake shaping, and cowling geometry even beyond World War II. Cooling problems didn't disappear after 1945. They continued into the early jet era, and many of the solutions, strategic airflow shaping, using existing structures to force cooling, trace conceptual roots back to experiments like the Hamilton Standard cuff. In other words, the cuff wasn't just a wartime fix. It became part of the aerodynamic toolbox. Another compelling part of this story is how few people today know about it. Ask most aviation enthusiasts why American fighters ran cooler in the Pacific later in the war, and they might mention better radiators or improved coolant formulas. They might talk about operational adjustments or the advantages of altitude. But very few talk about the propeller cuffs, even though field reports and test data from the period show just how vital they were. It's a reminder that history often overlooks the quieter victories of engineering, the ones without explosions, the ones without dramatic photographs, the ones that simply helped engines keep turning and pilots keep fighting. This forgotten innovation also illustrates the collaborative nature of wartime problem-solving. Engineers at Hamilton Standard, field mechanics stationed on island airstrips, pilots reporting temperature problems, and commanders demanding better reliability all played a role. It wasn't a single genius moment, but a collective effort, an iterative refinement born from practical necessity. Cooling issues were reported. Engineers brainstormed. Designs were tested. Prototypes were shipped. Pilots flew missions and sent back feedback. And slowly, a solution took shape, the hollow steel cuff that wrapped around the propeller root and quietly altered the future of Pacific air combat. There's also something poetic about the way the cuff works. It doesn't fight the air, it guides it. It doesn't rely on brute force, it uses shape and flow and subtle aerodynamic pressure changes to achieve a very practical goal. And in that sense, the cuff is emblematic of much of aviation design. Small, elegantly solved problems that together make the difference between a machine that barely functions and one that excels. So the next time you see a wartime photograph of an American fighter idling on a Pacific runway, take a closer look at the propeller. Notice the curved steel cuffs near the hub. Those seemingly simple shapes contributed directly to the aircraft's ability to climb into the tropical sky, engage enemy fighters, return from dangerous missions, and live to fly again the next day. They are reminders that in war, survival often hinges on the smallest pieces of metal, shaped with purpose, installed with care, and trusted with lives. In the grand sweep of history, it's easy to overlook such details, but the pilots who depended on those engines never forgot. They felt the difference in every climb, every dogfight, every long escort mission home across endless water. They knew, perhaps better than anyone, that victory is often built on things most people never see. And among those things, tucked quietly behind the spinning blades of America's most iconic aircraft, was a hollow steel cuff, an unsung hero of the Pacific Air War.